But functions are something that is one of the most important concepts that we have in math. And the notion of a function gets complicated when we start talking about sets, things like domain and range and all that. So hopefully today we'll cover it in a way that will make these things fairly clear to you. And we're going to end up talking about piecewise functions, which really, every time you go to the movies, you deal with a piecewise function. So we'll talk about going to the movies in a little bit. But to start out with, functions and relations. We don't really hear the word relations very much in a mathematical context, but a relation or a relationship is just basically, at its simplest, just basically any set of ordered pairs. So if I just say I have these these four pairs, this 1, 2, 4, 3, 5, 6, and 0, 6, I can say that that's a relation, because if I say, okay, what is the number associated with 4? You would look at that list and you say it's 3. What's the number associated with 0? And you would say 6. And that's all it is. There's nothing more complicated than that I've defined some sort of relation. Now you can see in a general sense, if we have a relation where, let's say, the first number is a year, the second number would be, let's say, the population of Moraga or something like that, then you could say, okay, in year 2012, what's the population of Moraga? And so we have real-world models that make use of the fact that we can make these relations. So the order of these numbers is very important. The first components, we're going to talk about that. The set of those numbers is the domain. All right, so the domain means these are all the numbers that are the input. If I were to say what is the number associated with 1, 4, 5, or 0, that's what I'm talking about is the domain. What are the numbers that this relation operates from? And then the numbers that are essentially the output, we're going to call that the range. And so our range here is 2, 3, and 6. Now notice I didn't say it was 2, 3, 6, and 6 because 6 is there. When we're talking about sets, we don't talk about repeats in them. We just list the ones in there. So the number 6 is 6, right? 6 is half a dozen, however you want to say it. And we say that 6 is in the range of this relation because it exists in the output somewhere. So there's no need to say that it exists twice. I mean, there's perhaps a need occasionally to say that, but when we're talking about the range, we're just looking at what are the elements of the set that define the output values of this thing. So we have a domain and a range. So the input is the domain, the output is the range, and it's not just the value, but it's the set of possible values. All right, so some people have a little difficult time remembering which one's the domain and which one's the range. Just remember, input is before output, and domain alphabetically is before range. So if you remember the two words, just remember the order. Domain is the first one, that's your input. Now, a function is a special kind of relation. A function is basically a rule that assigns each element in the domain exactly one element in the range. So what this means is that whenever I ask for the output or a value in the range, if I give a domain value, I should only get one value back. I get exactly one value back. And so if I list these things as kind of a mapping, okay, so I have 0 corresponds to 4, 3 corresponds to 2, 7 corresponds to 3, 12 corresponds to 1. This relation is a function. Okay, and I can list these as ordered pairs, 0, 4, 3, 2, 7, 3, and 12, 1. All right, so any number that I give you in the domain, you'll give me exactly one number back. Now, not every relation is a function. So here's an example of a relation that is not a function. If I map more than one value in the range to a value, or from the value in the domain. So in other words, if I say 7, and you're giving me back the number, you would say 3 or 12, right? And so my most important characteristic of a function is that it gives me exactly one value, and so it's not a function. It's maybe a valid relation, but it's not a valid function. So let's look at some examples in kind of the real world about what would be an example of a relation and what would be the example of a function. Okay, so there's a handful of car manufacturers in the world, but there's dozens and dozens of models of cars. So if I say something like CRV, you would say Honda. Okay, so if I give you any model of a car, and here I'm assuming that model names are unique, you're going to give me a manufacturer, and so that would be a function. So if I say Jetta, you would say Volkswagen, if I, anything like that. But if I said Chevy, or if I said Toyota, you could give me a whole bunch of different models of cars, and so that's not a function going that way. It's not a function to say when you have a car manufacturer and you have models of cars, because one car manufacturer can make many models, but at least with my assumption that every model number is unique, or model name, if I give you a model name, you can tell me what the manufacturer is. All right, so the way that translates into this is if I have a similar kind of mapping, and notice that 0 and 4 map to the same value in the range. This is a function, because it's not the range that has to be unique, it's the mapping from the domain to the range that is unique. So if I say 4, it's always 1. If I say 0, it's always 1. 7 is 2, and 12 is 4. So, we have this situation before where I could say, all right, on the right-hand side there, 7 maps to 2 different numbers, and so that's not a function because I get more than one number, but it's possible that that a function maps elements of the domain into the same number in the range. Okay, so that's a really important thing. Think about your calculator. Okay, there's many different ways to get to certain values there. Like you can do a number of expressions that'll get you to a 5 on the display. But whenever you do a certain sequence of numbers, you only get one calculator. I'm talking about ordinary calculators of multiplication, division, subtraction, and addition. Where if you put in 4 plus 2, it only gives you 6. And so this is the sense of a function that we're talking about mathematically, where the value is exactly one value. Okay, so that's written out, hopefully, what I just said. So then we have a way of writing functions, and we'll call this notation. And I think most of you have seen this already. You have f at x, and we think, okay, there's a function. Now, the thing about this notation is that, unfortunately, we only have a few ways of writing symbols. There's only a finite number of letters in the alphabet. There's only a few characters, relatively few characters on a keyboard. So this could mean two things. This could mean f times x, right, because we use parentheses to denote multiplication, if f is a variable and x is a variable. But it also means f is a function evaluated at x. And this is one of the reasons why I ask you always to define your variables, because now we got to not only define the variables, but we got to define the functions as well. So we know if you just look at that, is that truly a function, or are we just by coincidence having this variable f that multiplies to h, or to x. So this is the name of the function. F in this case is the name of it. And then the value that you put in the parentheses is a value from the domain. Now when we use a variable, that means we're choosing a value in the domain. We're not saying that x is in the domain, some value that x equals is in the domain. So the way we would read this is that the function in this example is f. All right, contrast that with the value of f evaluated at x is f at x. All right, so the difference here is that, and I can say f of x, and sometimes I say f at x. They're both common and they're both the same thing. The difference here is that f at x is a value. F is the function. Okay, there's a subtle difference here. When we talk about what function do we have f as a function. What's the value of the function? Well, f at x equals, or you might say f at 1 equals, or f at 2. So whenever you put the argument in there, you are suggesting that it's a function, but really what you're doing is you're stating it as a value. So we put f at x in equations, because equations have to have values in there, right? So we say something like f at x equals 2x plus 1. Well, that may be the definition of f at x, but we talk about f as being the function. F at x is the value of that function evaluated at x. All right, so let's take a function here, a fairly simple function, f at x equals 2x plus 1, and we're going to evaluate this at different points. And so what that means is I'm going to say, what's the value of f at 0?
1.
Yes. Okay, so the way I'm going to suggest that you do this is that you write the function's definition, and instead of writing the variable, write a parentheses where the variable goes. And then afterwards, write in what that variable's value is, and then calculate it from there. So in this case, you could do it in your head, right? You put in a 0 and you get 1. But just to kind of illustrate my point here, I'm writing kind of this template or this prototype of the function, and then I insert the value that's within the parentheses. Okay, so f at negative 3. Now, where this gets tricky is where you have negative signs and squareds and all this kind of stuff. And so the reason why I'm suggesting that you use this method is that you're going to break a mental exercise that you can make mistakes on fairly easily to one that's a little bit more reliable. So all we do is the same thing. We're going to write first what the function is, then we're going to insert the variable's value, and then now we have a completely different kind of problem. This is just a simplification problem. Everything is there, and so 2 times negative 3 is 6, and we add 1 to it was negative 6, and we add 1 and we get negative 5. Now where this comes in handy is where we have expressions. Like if I just say, okay, what's f at t? And you might think, well, what is f at t? Well, if I've defined f at x equals 2x plus 1, I do the same thing. I can say, just put t in here, and so f at t is 2t plus 1. That could also serve as the definition of it. The variable letter that you use in there is not very important. It's just, it corresponds to whatever's in the parentheses is evaluated in that expression in that way. And so let me write one more on the board that's just perhaps the next level of complexity. If I write f at x at, let's say, t plus 7, all right? So I can use the same method where I'm going to say, okay, it's going to be 2 times whatever's in my parentheses plus 1, and I just insert the t plus 7. And from there, I can simplify then. So now I have 2t plus 14 plus 1, and so that's going to be 2t plus 15. And you see, this is a kind of a shift from just calculating the number to saying, okay, what is the equivalent expression in this variable? So I've put in t plus 7 here, and I get out something that is not a value, but I get an expression involving t. And so this is one of the ways that you can use this reliably. The other instance that you're going to that this will be helpful using this method is if we have a function that has the variable in more than one place. Like if we have this this version of f at x is 2x squared minus 1 plus 1. If I write out, let's say I want to evaluate it at 1, I can write it out first, with parentheses only, and then I'll drop in my variable there, 1, and then I can calculate 2 times 1 squared is 2, minus 1 plus 1, and so I get to 2. And so if I have something that could potentially trip me up, like I have a negative 2, and notice I have a negative x, so I'm going to be dealing with a double negative in there. Don't do that in your head. Just write out exactly the same kind of framework for your function, and then drop in the value, and now you have a much different, a much simpler problem in being able to reliably calculate what this thing is. So now we just calculate each individual term, 2 times 4 plus 2 plus 1, we get 11. Okay, so I'd like you to try this one. How's the sign-in sheet? Did everybody sign it? Good, got everybody. All right, what did you get? Excuse me? Negative 1, very good. Okay, so if you did it the way that I've been advocating, you would write the function without the putting in parentheses instead of the variable, drop in what you have in your, within the parentheses, and you get a negative 1. So negative 2, it's essentially the same kind of exercise, so I'll do that one here. And so there's my function, and I'm going to drop in a negative 2. Simplify that to be 1 over negative 3, which is negative 1/3. Okay? All right, so let's try now f at 1. So if we do f at 1, what we get, if we start the same way, drop in the 1, and we get 1 over 0. And here's a problem, right? Because this is not defined. This is undefined. So what does this mean when we get an undefined number? What it means is that 1 is not in the domain of f at x. It's not in the domain of f, I guess, if I really want to make my distinction between f and f at x, right? So remember what the definition of our function is that it takes a value from the domain and assigns a value in the range. Well, there's no assignment that's possible here, so 1 is not in the domain. And so we can refer to this as, as x cannot equal negative 1 as a domain restriction, or we can define the domain that in a way that says we can't use a 1. So when we just have an expression that doesn't compute, okay, we know that the function has a certain domain just by what works and what doesn't work. Now, there's times that we want to have what's called an explicit domain, and we'll see an example of that. But in essence, if, let's say I have a function, I'll jump ahead a little bit, our movie function will be, what's the cost of seeing a movie? And so the domain of that thing is going to be your age, and so the domain of that thing is your age has to be more than 0, right? I mean, there's no movie theater in the world that I know of that has posted a negative age, because people aren't negative ages, or at least they don't have to pay for movies if they're a negative age. So that's a different case. That's where we say explicitly what the domain is. Implicitly, we're saying what works in the function and what doesn't work in the function. So with this particular one, the first one that we looked at, this f at x equals 2x plus 1, every number works in there, right? You can multiply 2 times any number, add 1 to it, and you get a number, and so it works. And we'll say that these are, the domain here is all real numbers. There's 2 other ways to write that. We've seen interval notation. Excuse me. Okay, we've seen the interval notation where it's minus infinity to infinity. Or we can use that peculiar looking r. And that r just means almost universally in math books and among mathematicians as meaning literally the set of real numbers. Okay, so you see that R and you read that out loud as the set of real numbers. So let's look back at that function that we have before, that 1 over x minus 1. And so the domain is all real numbers, but x cannot equal 1. So we can write that in interval notation as the union of two intervals, negative infinity up to 1, and then from 1 to infinity. And since I put the curved parentheses rather than the square brackets, that means that I'm not including 1. So that's one way to write it. And interval notation is nice in that way because it gives you an idea of where the function works and all that kind of stuff. But there's another way to write it, and I'll give you a few examples of this before I really tell you what's at the core of this. Okay, so we can say this is the set of x such that x does not equal 1. That's the way that reads. All right, so let's look at a slightly different function here. We're going to take the square root of x minus 1. Now, what we know is that to take a square root, it has to be 0 or positive, right? We can't take the square root of a negative number. So we know that x minus 1 has to be greater than or equal to 0. And so if I rearrange that, I'm going to say x is greater than or equal to 1. Well, this tells us right away what our domain is, right? Our domain is going to just be the interval from 1 to infinity. 1 works because you got 1 minus 1. The square root of 0 is a perfectly good number. That works, and any number that's greater than 1 works. If we take any number that's less than 1, let's say 1/2, we have 1/2 minus 1 gives us a negative 1/2, and we can't take the square root of that. So we can call out its domain in interval notation, or in what I'm going to call a set builder notation, is that this is the set of x such that x is greater than or equal to 1. And I'll break this down on the next slide, exactly how this goes together. But in the meantime, find the domain of this function. And I'm really not too particular right now about how you express that. So let's just think conceptually. What would be the domain here? So the domain are all the numbers I can stick in here and get a number out of it. Where does it evaluate? And so sometimes looking at the exceptions is better. Where does it not evaluate to something? What do you think? Anybody have an idea?
Could you ask that one more time?
Okay, what are the values, or what's the domain of this function, which means what are the values that work when I put it in as x? Well, let's just go through some numbers and see if we can figure out which ones work and which ones don't work. So let me say x equals 0. Okay, so if we have a 0 in there, we have 2 times 0, which is 0, divided by 3 minus 0, which is 3. So we have 0 divided by 3. That's a perfectly good number, 0, right? Oftentimes people want to exclude 0 from the domain when there's no need to. It's a perfectly good number. But let's look at the denominator of this thing. Okay, so we're going to have basically two areas that will cause us domain restrictions, things that will be numbers that we can't include in the domain. The first one is going to be what we've seen in that second function, f at x equals 1 over x minus 1. That's where we end up with division by 0. And then the second one is where we try and take the square root of a negative number, and that's that second case. So if we relook at this function that I'm asking about now, this f at x equals 2x over 3 minus x, where are we going to run into trouble? Well, we don't have any square roots, so we're not going to run into any trouble there, but we have a division, so we know that the denominator can't be 0, right? So if the denominator can't be 0, then 3 minus x can't be 0. So what's the value of x? It's 3, right? Because 3 minus 3 is 0. So the way I'll state the domain here in just ordinary words is all real numbers, x, such that x does not equal 3. Okay, maybe that's not so real world English. That's not the way you speak, right? You'd never use that sequence of words. But hopefully if I say it, maybe you understand what I'm meaning. So all numbers fit except x cannot be 3. Now we end up with a double negative. And notice I hesitated. So if I say all real numbers except x cannot equal 3, shouldn't I be saying all numbers except x equals 3? So that double negative in there, that except in there, is just bad form, okay? I mean, maybe you can work it out logically in your head, but I guarantee you if you work it out, maybe the reader who's reading your work won't work it out. So this is very clear. So this is saying that x such that x does not equal 0. So we have one single negative, x does not equal 0, x does not equal 3. So that phrase such that sounds a little pretentious, and admittedly it is, and it's not part of our normal conversational English, but those are going to be the choice words that we use when we describe anything about a set, whether it's the domain or the range are the two sets that we're going to be most interested in. Okay, so let's look at ways of notating a domain again as a set now. Okay, so I already said that funny looking R, that's the R with the double back in there, that's the set of real numbers. And so you might see that in a textbook or something when you see that R, and it always has this kind of, it looks like it should be colored in bold, but it's not. It's like a double stroke on the back, and sometimes they have a little double stroke on some of the other parts of it. But very clearly that's the set of real numbers. Now other numbers have their different symbols as well, and we're really not going to get into them, but like integers has the same type of letter for Z. Rational numbers, you would use the same kind of letter, but a Q. Some of those things that we've probably talked about at the beginning of the semester. But the one that's really going to play into us is going to be the set of real numbers. Okay, so we can also use interval notation, and you've all used this a little bit so far in this class, so I won't necessarily go over everything about that. It's this set builder notation that is perhaps new. We call it set builder notation because we're just doing that. We're building a set. All right, so this isn't really that hard. It just looks bad. Okay, so that opening brace there, it's always a brace. You just read that as the set of. Okay, so just translate that into plain English as the set of. And then, of course, x is x. And then this vertical bar means such that. Okay, so the set of x such that. And at this point, we're wide open to any kind of description that we want. Okay, so we can put in particular values. If the function only works for two values, we can say the set of x such that x equals 1 or x equals 2. I mean, it could be that simple. With this particular example, we're saying that x is greater than or equal to 0. Now I put just greater than, but you can see from the symbol there it should be equal, greater than or equal to. So it just reads like a sentence. And then the brace closes just like a period at the end of a sentence. So this framework of just having the brace, a variable, a such that, and then whatever goes in here is the way you would describe it. You can put things that you include or things that you exclude in here. So you can put x does not equal 1. You can put in x equals 1. What you don't want to do is name another set in here. Like you would never do this. You would never do this. Because the way this reads is the set of x such that the set of real numbers. Okay? That doesn't really make sense. All right? So if you just want that, you can write something like this where x is an element, and this is kind of a funny looking E of that. And we really won't get into that too much either, because we're going to assume that we're always dealing with a real number. So if you want to say all real numbers, just go to that R. Okay, that's the way to do it. If you have any other things in here, any qualifiers, like let's say x is greater than or equal to -1, and that x cannot equal 0. That's a perfectly good description of a set. So we have two different conditions, and in interval notation, of course, this would look like this, which I think is far more complicated to write out. So this would mean from -1 to 0, and then from 0 to infinity, and we're not including 0. That's why we break up the two intervals. So this actually, in the long run, I think will serve you better as being an easier way to read a set, and it's certainly, I think, an easier way to construct it, because all the things that you come up with, the list of things that it's either supposed to be or not supposed to be, you can just throw in there, separate them by commas or the words or and things of that sort. Okay, so I'd like you to write the domain of this function. F at x equals 1 over x times 1 over, 1 over x times x plus 1. Okay, so there's a start. Now you said all real numbers such that. So do we really mean this? Right? All the set of x such that x does not equal 0. Okay, that's good, because we're going to get, if x is 0, then we have 1 over 0. But also, x can't equal -1 as well, right? Because if x equals -1, then we have 1 over -1 times x plus 1. So here we have, if this, we know that we can't have, this can't equal 0. Okay, but we also know that this can't equal 0. All right, so it's not just x, excuse me, it's going to be x plus 1 cannot equal 0. And so that what that means is that x cannot equal -1. And so we'll make this a list like this. Now, if this escaped you a little bit, we're going to talk a lot about what makes things 0, you know, and it's called the zero product principle. Don't worry too much about that. Really what the exercise was about was to get used to the notation that we'll start out with this, the set of x such that, and then we put in our list of domain restrictions, and then we close it off like that. All right? Any questions on that? Okay, let's talk about the movies. I said earlier we'd talk about the movies, and let's, so you go to the movies, and invariably there's a sign that looks something like this, where you go up and you say, oh, depending on what age you are, it's going to cost something different to get into the movies, all right? And so mathematically we call this a piecewise function. And so probably a little bit more generally, what a piecewise function is that a function that has a definition, just like any other function, but this one has definitions that change depending on the segment of its domain. And so what I mean by that is that if a equals the age, then the domain of the whole function is going to be a such that a is greater than or equal to 0, right? We're going to start with infants, and we're not going to put an upper limit on it, although there's probably a practical upper limit, you know, 120 or whatever you want to put there, but we're just going to say it's open-ended. And so then the parts of the domain that we're looking at is when the domain is, when a is less than 14, when it's between 14 and 65, and when it's over 65. Now, depending on how the sign is worded, it could be under 14, or it could mean to include 14. Mathematically, we have to be precise about this. Just like if you go to the movies and you say, okay, I'm 14, the person who's going to tell you what it costs isn't going to say, well, it's $5 or $15. They're going to say one or the other. And so when we're piecing out our, or making our domain into pieces like this, we want to make sure that we don't overlap, that we have these three, in this case, parts of the domain where A is true only in one of the cases. So either you're under 14 or you are 14. And so in this case, when you are 14, you're paying $15. When you are 65 years old, you're paying $15. If you're over 65, that means you're going to pay $10. Okay, so those are the pieces of the domain that we're going to think about. And so I'm going to say, let's have C at A is the cost of admission. This is a function of age. All right, so let's say C of A. You give me an A, I'll give you a C, kind of a thing. So if you say I'm 20, the C at 20 is going to be 15. And so you can, we deal with this kind of thing a lot, right? I mean, where you just look up what particular value pertains to what you're doing. And so the way we're going to write this mathematically is a little bit backwards from the way that you typically see it in a sign. Is that we're going to say these values that are after the comma are the pieces of the domain, and depending on what piece is true, we're going to look at the first column and say that's what our value is. So the way we would read this is, okay, if I'm 22, I wish I was, but if you're 22, then the first one isn't true. A is not less, your age is not less than 14. It is between 14 and 65, but it's not more than 65. So it's the second line that's true. And so we look on that second line and we see, okay, our function is defined, in this case as a constant, C at A equals 15. All right? Now, in different books, you'll see this thing written slightly different. And what they'll do is instead of just writing a comma right in here, they'll put the word if. And perhaps that's clearer if you want to think about 5 if A is less than 14, 15 if 14 is less than or equal to A is less than or equal to 16. So sometimes you see the word if in there and sometimes you don't. It's really up to the author. And so the second column is always the part of the domain, and so that's the value of the function, is what's in front of it. Okay, any questions about this? Now, we can make these piecewise functions expressions too, and the expressions don't have to relate to one another. Some can be constants, some can be expressions, some can be just anything that we define there. So probably a good one to start with is the absolute value function. We all know what this does, right? If you take the absolute value of -4, you get 4. If you take the absolute value of 4, you get 4. So this makes for a good piecewise function, and we're going to define it this way. We're going to have negative x if x is less than 0, and we're going to have x if x is greater than or equal to 0. So in other words, if I have a negative number, I'm going to take the negative of that negative number. And if it's a positive number, I'm going to leave it alone. I'm just going to return x. Okay, so that looks a little confusing, perhaps, with the negative x. Why do we make it negative if it's already negative? Well, let's evaluate that. Okay, so if we have f at -2, so which line corresponds to x at 2? Okay, so we choose between these two, and we know that x is less than 0. So then our function then is defined as f at x equals -x. All right, so we choose the line that's right, we make that the function definition from there, and then we stick it into our function, and you can see what happens if I write it the way that I'm suggesting, is that you instead of the variable, write parentheses and then drop whatever in the function expression in that. I get -2, which makes that 2 then. Okay? And of course, we usually see this as just the absolute value of -2 is 2. Okay, so here I'm going to define a piecewise function in 2 pieces, and I'd like you to evaluate these 3. And I will most definitely call you by name on this one. So evaluate those 3, and then that will kind of conclude what we're talking about for today with piecewise functions.